Alright, today we're going to do an odd half-range expansion for this function f of x equals pi over 2 from 0 to pi over 2 and pi minus x from pi over 2 to pi. Alright, so first let's go ahead and graph the function, and I've done that for you already in Desmos. And what we see is that it's a constant value from 0 to pi over 2, and it's a slope of -1 from pi over 2 to pi. I just kind of want to show you guys what's going to happen here when we do an odd half-range expansion. Basically what's going to happen is we're going to take this function, copy it, and paste the negative value on the left-hand side. So ultimately this is going to be the function that we want to project onto a Fourier basis. Alright, so what happens if we project this function onto sine? Well, we can see that all we really need to do is look at the right hand or positive side, because if we project this function onto the sine on the positive side, then naturally what's going to happen is sine is going to copy this projected piece and it's going to make it negative on this side, because sine is naturally an odd function. So let's get started, and the first thing we're going to need to do is define our period. So from here we can see that our period is going to need to be this whole entire function from -pi to pi. Because we're working with half periods, all we're really going to be concerned with is from 0 to pi. So let's get to it. Alright, so I copied the piece of graph we care about. Now what we need to do is just write down our general equation for an odd half-range expansion. And that's going to be the coefficient Bn equals 1 over L, integral from 0 to L, of f of x sine of n pi x over L dx. So the only unknown we have here is L. We can find L just by saying that if the period is equal to 2L, and this is half of the period, then we can say that the beginning of this function would be 0 and the end of the function would be L. Alright, so now what we're going to do is just plug in what we know about L, and we're going to say that Bn will be equal to 1 over pi all times the integral. Okay, so here's where it kind of gets weird. We need to make sure that we split up the integral so that we define this area and this area separately. That is, because this function is piecewise, we need to define the integrals separately. Okay, so how we're going to accomplish that is by taking the value for the function here and evaluating them on the integral bounds here and here. So let's do that here. We got integral from 0 to pi over 2 of pi over 2 sine of n. Well, what happens here is we get pi over pi, and that cancels to 1. So we're going to just have sine of nx plus the integral from pi over 2 to pi, and that's going to be pi minus x times sine of nx dx. And don't forget your dx here. Alright, so now what I'm going to do is have you pause the video and go ahead and do these integrals out. And when you do these integrals, make sure that you solve the integrals exactly. That is, don't simplify pi over 2 into a numerical answer. Alright, so if you've done your integration correctly, you should get the following terms, and if you need to, just go ahead and check yourself. Alright, the next thing we're going to do is make a table. So the idea here is that we evaluate each one of these different terms separately. Okay, so the idea here is we're going to evaluate only the trigonometric terms, sine and cosine, for these n values, and we're going to see how these n values will change the coefficient out in front of the trigonometric term. That means that any n outside of a trigonometric, we're going to leave that as a variable and only change the n's that are within the trigonometric term. Alright, so let's evaluate the first row for cosine of n pi over 2. And we're going to see that when n is equal to 1, we're going to have cosine of pi over 2, which is going to be 0. So we put a 0 here. And when n equals 2, we're going to have a cancellation from n and 2, and we're going to have cosine of pi, which is negative 1. So we'll put negative 1 over n. And for 3, we're going to have 3 pi over 2, which gives a 0 value for cosine. We're going to have 4 pi over 2, which is cosine of 2 pi. It's going to be a positive 1, which makes this a 1 over n. Now, following that same logic, I'd like you guys to pause the video and go ahead and fill out the rest of the table here. Alright, so this is our values that we come up with, and what we're going to do from here is evaluate how the coefficients alternate in sign, and we're going to do that by looking at the odd channels, even channels, and all channels. The first thing we're going to do is identify the fact that n equals 1 and n equals 3 are both odd values for n, and we can say that the odd channel is therefore the first channel where n equals 1, and the third channel where n equals 3. So the even channel will be for n equals 2 and n equals 4, and the all channel is evaluating all of the channels simultaneously. When a function is only defined on an even or odd channel, we're going to separate them into their respective channels. Now this might be a little bit easier to write out, so let's do that. So let's evaluate the odd channel. So for the odd channel, we can see that this function here only exists on the odd channel, right? It exists when n equals 1 and n equals 3, and has 0 values for even terms on n. So it exists on the odd channel. So let's first define the odd channel by saying that any n value in the odd channel will be defined as 2j minus 1. Why are we doing this? Well, we want to make sure that when we evaluate this, we want to do it as efficiently as possible, and we also want to make sure that any terms that could be evaluated by mistake are not. In other words, we don't want these zeros to be multiplying our equation later, which gives us an incorrect result. Alright, so what we're going to do is first say that because this term here is positive, we're going to come down and say this is going to be negative 1 to the j plus 1. And the most important thing to realize here is that we're basically combining these two rows and making this j equals 1, and this here down here j equals 2. Basically that's what we're doing for only even and odd channels, and then for all channels we're just going to say that n equals j, so this will be j equals 1, j equals 2, j equals 3, and j equals 4. But that's only going to be for when the function exists on all channels. Alright, this is kind of a weird concept, and if you don't understand it right now, hopefully by the end of this example you will understand what's going on. So we're going to keep j plus 1 because we want to make sure we evaluate both of these channels at the same time, which means that this function here will be modified, and we're going to write 2 divided by pi 2j minus 1 squared. Now see what I did here is I substituted n to be defined as 2j minus 1, which is an odd value for j, which makes the odd channel always exist for j. Alright, so now we have a general equation for this column, and we need to make a general equation for all the others. However, there's a little bit of a cancellation that can happen here, and you have to be very careful about this. If a function on two different columns evaluates the same coefficients on the same channel, right? So this is the even n channel, and this is another even end channel. And we can see that this function evaluates to a coefficient of negative 1 over n, and this function here evaluates to 1 over n. So we can see that for every value of an alternating coefficient, we will always have a complete cancellation. Now what I'm trying to say is you need to be very careful about the situation where you have a negative 1 over n and a 1 over n in different channels. Now because the all channel spans both even and odd, we need to make sure that these coefficients are not affected by cancellation from other values. Only cancel terms if they're in the same channel, and they will always be the negative of each other. So now let's work on the all channel, and we'll see that we'll have 1 over n as the coefficient, and it's non-alternating. So for the all channel, we're going to say n is going to be defined as j, so we'll have 1 over j. The next step is just going to be looking at our summation for our Fourier series, which is a0 plus an cosine of n omega x plus bn sine n omega x. And we can see that a0 and an will both go to 0 because we have an odd function. Okay, so all we care about is summation of bn sine n omega x. But in this case, omega is 1. So we have the summation of bn of sine nx. So what we need to do is say that our bn is also pretty much a piecewise function, where bj are these two coefficients. What we need to do here for this summation is also change the n inside of sine nx so that it equals our odd channel and our all channel. What that's going to look like in the end is something like this. And we're going to say that j will go from 1 to infinity, or we can make this finite and say j will go from 1 to k. Alright, so let's look at what we did here. We took the odd channel and we defined n in the odd channel to be 2j minus 1. So then we came and said that we need to alternate for every j, starting with a positive value. And then we have n defined to be j for an all channel. So bj is going to be split up into two different channels. And for the summation, we need to make sure that our odd channel has sine with an odd n, and our odd n equals 2j minus 1. And our all channel, we want to make sure that we define n to be j here. And this will be the final form of our equation. So let's go ahead and put this into Desmos so we can graph it. We can see how our function should look. And let's take k to be 1 at first. So for k equals 1, we're just going to have our sine term, and we're going to basically take this sine basis and project it onto our function. And for one term, we can kind of just see that it's going to do the average of the function a little bit. So let's take this k term and ramp it up a little bit. So for k equals 2, we see a better approximation for our function, but that just means that we have a 2-term basis to work with. Next, let's ramp it up a little more. Alright, for k equals 6, we can see that we're converging to this line right here pretty quickly, but we still need to converge to this horizontal line. And we can see when we add more terms or more basis functions of sine, basically we're going to converge after an infinite amount. And if we take a finite amount, just 100, we can see that right here we're going to have a point of discontinuity in sine, and what happens is there's going to be an over approximation for sine, and then that over approximation is going to die down with an exponential curve. We're going to have this extreme oscillation at points of discontinuity, and that's called the Gibbs phenomenon. This is a very important concept in terms of signal processing and how we can compress digital files. One more thing I'd like to show you is that we can split this signal up into two different functions. The function in the orange line, we can see that that's going to be the odd channel, and this odd channel spans just like an odd function would. And we're going to have the all channel, which is the channel that defines the discontinuity or the Gibbs phenomenon. So if you had any trouble following along with the concept, or you had any general comments on how I can do better next time, just please comment below and I'll try to fix whatever I'm doing wrong. And as always, please share, like, and subscribe my videos to anyone who likes to do crazy math. Alright, later.